Hello, I'm Kyle. I'm the technical content developer at Maple Systems. Welcome to the Maple Systems video training series. In this video, I'll be showing you how to simulate the PID loop function in Mapware 7000. I will be using an HMC 4000 series, specifically an HMC 4070. In this sample project, I will be simulating how a PID controller controls a water heater that can heat liquid to a desired temperature and hold that temperature while accounting for some natural cooling from the environment. Here is a PID loop example using a water heater. You can also find this diagram on the How to Program a PID Loop tutorial page on the Maple Systems website. So before I show you how I created this project and showing you how I created the PID loop function, the basic idea behind a PID controller is to read a sensor. Then it computes the desired output by calculating proportional, integral, and derivative responses, which is what PID stands for, and then summing those three components to compute the output. And here is that PID function. And I just want to give you an overview of what this is. So I present the problem up here. We want to raise the temperature of a liquid from 100 degrees to a steady 250 degrees. So naturally the environment will cool the liquid, like I mentioned in the beginning of the video. So the solution is creating a PID controller, which we can easily and quickly manipulate a heater to keep the temperature at a constant 250 degrees. So the PID controller receives the process variable, so PV, and controls the manipulation variable, MV. The manipulation variable is also the PID output, which controls the actuator. So the PV controls the MV in order to adjust the PV, the process value, to match the set value, so the set point here. So one, the proportional gain. So the higher the proportional gain value, the faster the controller responds. So if it's too low, if the proportional gain is too low, the controller reaction speed will be too slow, and it may not be stable at that point. Too high, the controller may overshoot and start oscillating. So integral gain, the longer it takes to reach the set point, which is right here, the more the integral influences the output if the proportional value is small, for example. Too low, the controller may never reach that set point. It's very slow. Too high, the controller may overshoot and start oscillating. The derivative gain limits the output to prevent overshooting. So if it's too low, if the derivative gain is too low, the controller may not be influenced and does not limit the overshooting. Too high, the controller may become unstable and have undesirable reaction to distortion on the actual value. Okay, I want to explain what each of the inputs for your PID loop function. So I have project open in two different windows here. I want to show you the function block as well as the tags I created for that function block. So the first one is auto, or I also call it start, to have a start bool here. So it determines if automatically tuning or manual. So in this case, we'll be doing a manual tuning in Mapware 7000. It really does not have an auto tune function. The PID loop function is a manual tuning function. That first tag here is to change it from auto to manual, but truly it is a manual tuning function. PV, the process value. SP is their set point. The X out underscore manual is the output value in manual mode, and KP or K gain is the proportional gain, TI is the integration factor, and TD is derivation factor. TS is your sampling period. So the sampling period is a time register. So an Xmin, an Xmax. Xmin is the minimum allowed output value, and maximum output value is the Xmax. And then here are some on and off bools. You have integration enable bool, integration value freeze bool, integration reset to initial value bool. The integration enable bool is if it's false, the integrated value is ignored, and it must be set to true for the integral control to function. So the integration value freeze bool, so if true, the integrated value is frozen. Integration reset to initial value bool is if true, the integrated value is set to the integration reset value. So if this is true, it is set to the integration reset value. And the integration reset value for integration when this is true. This has to be true for this to be initialized. Then we have the deadband error, also called hysteresis on process value, or PV. It's the lagging response to the output. Then there's also the FFD, which is the disturbance value on the output. So you can manipulate this to affect the output. So these are all the inputs for the PID loop function. There are also some outputs, and I'll go over those. So the X out is obviously the output value. ER is the last calculated error. So the X out P, or the calculated proportional value, and then you have the X out I, which is integral value, and the calculated derivative value is the X out D. And then here are also some on and off bools. X minimum saturated. This is true if X out is equal to X min. And then the X out LLM is true if X in is equal to X max. So if X min is equal to X max, this is true. If the X out is equal to X min, this is true. Now for Mapper 7000, in this case, the analog output minimum is 0 and the maximum is 4095. In this case, it could be different for what you're using. So this is just a scale in function to take the raw value and scale it to a real value. So for the input, I have an output value tag here. 0 is minimum, 4095 is the maximum, and it's between 0 and 100 for the output minimum, output maximum. And then this is the scaled value, scaled output value. And then I'm also using an addition function here. So this is the process value and the scaled output value added to the process value. So I explained all the tags that you need to create for the PID loop function, as well as the scale in function and the addition function here. So this is all you'll need for your main logic block. I also have a subroutine for the temperature loss simulation. So I create another rung here and another tag, and it's an enable temperature loss. And I created a subroutine. So to do that, you go to subroutine, create one here. I called it temperature loss simulation. So this is just simulating the temperature that's falling. For example, if the natural process, such as leaving your mug of coffee on the table. So here I have a pulse timer, and then I'm using a division function and a subtraction function. And so I'm taking the process value, it's an input, and 100, which is the temperature we're starting at. And then the output is the temperature loss. So it's a division, and then subtraction, the process value, and the temperature loss, and then minus the process value. In my main logic block, I'm taking that subroutine. So to do that, you go to the project folder, take the subroutine, and drag it into my function. So I'm going to go to my base screen, and I named it input outputs. So here are those tags that I showed you in the logic block. And so I'm using a data entry for each of these, and these are assigned to the corresponding tag. So process value is process value. And I don't have a maximum or minimum set here. And the data type is a float, so I can show positive, negative, or a decimal point. So the other tags I created, I didn't mention yet, are some buttons that I created here. So this will start the process. This is integration button, and these are the integration holds. And as well, I have those X min and X max saturated buttons here. And for the start auto button, I had to create a few tasks. So to do that, go to the tasks here, drops down, and I created write 0 to tag elapsed time 1, turn bit enable temperature loss off, and turn bit integration reset the initial value on. So when it presses and then when it releases, I have a toggle bit start, turn bit timer bool on, toggle bit enable temperature loss, and turn bit integration reset the initial value bool off. Now to create a press task and a release task, you'll check off press task, and then let's say you want to create this one here. So you do write value to tag, and then you choose that tag, which is in this case elapsed time 1, and then you would write 0 and then hit add. For turning a bit off and on, you would choose turn bit on or off, and then select that tag and then hit add. Same thing for release tasks. Just make sure you have release tasks selected. And let's say for the toggle bit, you'll just select toggle bit and then choose that tag and add it over. So these are just different functions I want to have for the user interface when pressing this button. And then these are bit lamps. So these will turn on when certain minimum, maximum are reached. So I assign these to the Xmin saturated tag and then the Xmax saturated tag as well. And then also I want to have a graph to show our results. So when we start this, we want to see the results of our PID loop. This is a trend that I created here. So to create a trend, you go to Advanced Objects, then Real-Time Trend will show real-time graph. The tag I have assigned to it is the process value. And then I'm showing from 0 to 400, just so I can show temperatures between 100 and 250 in the middle here. And maximum values 400 is here, minimum is 0, of course. 10-second time, actually going to change this to 30. Here I have the enable bit button here, temperature loss. Tag name is enable temperature loss. And then I have an integration reset to initial value button. And all these can be edited. They're all data entries, so you can change the values. So after you create your user interface screen or your base screen here, and at this point, you can download and go online. So to do that, go to mode, go online with download. If you are downloading for the first time on your 4070, make sure you have firmware checked off. If you've already downloaded once, you can just have application checked off. So in this case, I've already downloaded once. Hit download. And in the compile window, it will say run. That's how you know you're online. And at this point, let's simulate this PID loop function. Okay, so now we are online and looking at VNC Viewer. So this is the actual user interface. So let's click on the PID inputs and outputs. So here's our base screen that we created. And we have our sampling period set to 100 and the set point is 250. Let's set the process value to 100. This will be our starting point. And you can see the difference. Calculation error is 150. So let's go to our graph. We can adjust this here as we go along. I've already figured out what the best calculation is here to get a ideal PID here. I can simulate an overshot as well as ideal just to show you an example. And so let's go to the graph screen, go to next. And so I want this set to 100 and this is set to 250. Now I want to show you an overshot. So let's set the proportional gain to, let's say 8. Integration gain, we'll leave it 3. And let's set the derivative gain to 0.2. Hit OK. And let's start. And you can see it overshot. And then it's going to go back down. And now it's oscillating and leveling out at 250. And so that shows an overshot. Now I have figured out what an ideal setting is here, so I'm going to show you that. So I'm going to disable, and then temperature loss is off. It's going to go down. So let's set this to the ideal numbers here. So this is 4. We'll set this to 3, and this will be 0.1. And make sure before you test out an ideal path, you have to reset the process value to 100, set point to 250, hit enable. And you can see how that was pretty good. Shot up to 250 and oscillate a little bit, but that's a pretty good line there. The ideal pathway was proportional gain was set to 4, integration gain was set to 3, and we set the derivative gain to 0.1. So this is how you would set up a PID loop in Mapware 7000. This concludes the video. To get more information, please visit the How to Program a PID Loop tutorial page on the Maple Systems website. Thank you for watching.